trop les tissus In-silico. Pour moi, c'est une bonne façon d'apprendre des choses sur les tissus et d'utiliser les tissus. Et donc, je le remercie d'avoir accepté de venir.
Oui, merci pour l'invitation, mais malheureusement, mon français n'est pas à la hauteur pour présenter en français. So I'll switch to English for the rest of the talk. I hope that's fine for everybody. I guess the announcement was in English, so I guess you're expecting me to speak English anyway. So what I want to convince you of today is a sort of a bit of a different style, going a level faster than the lecture, the beautiful lecture we just had. It's going to be a bit of a roller coaster ride through what you can do by using simulations to study tissue mechanics. So as you heard from in the lecture just before, the idea that mechanics influence growth is not my idea, and it's not new. This is this paper that was just mentioned here by Schreiber in 2005, where he coined the idea that maybe forces regulate the growth of cells and tissues. And there's other famous biological examples, which I think you will hear a lot throughout this lecture series, of mechanics influencing tissue growth. Here, for example, people have shown that the closure of the amniserosa on the fruit fly is regulated by a lot of different mechanical forces. Another example is by a friend of ours here sitting in the lecture room as well, Pascal Sebazan, with a lot of other co-workers actually, where they studied how one tissue invades another one by motility forces and, well, mainly motility forces, I think, and some growth compressing and so on. And the mechanics is really the key factor here, how these pink people can invade the green ones. So I think you're going to hear a lot more about the biology and mechanics connections, so I'm mainly going to skip over that. Instead, I want to look a little bit at the theory, and I think that part that we didn't hear today that you're going to hear next week is this one part where you say that this term, that K that is here and that appears everywhere time and again, might actually depend on mechanics. And then the theoretical approach that I guess you will hear is to say, it comes from a simple Gedankenexperiment. So think you squeeze a tissue into some magic box that can somehow contain the tissue and keeps it alive and happy and nutrient and so on. And then the tissue grows and starts to push on the side walls, right? And then let's say one of the walls is a movable piston, then you will compress that piston, compress the spring, but eventually the restall force of that spring will be so large that the tissue can no longer grow. That should be a well-defined pressure, which we call the homeostatic pressure. And then for the whole calculations that you can do here, you can write a simple equation, which is K, that this net growth rate, right? KD minus KA equals some prefactor kappa, pH minus P. So I'm not going to explore this equation a lot because I think you're going to hear about that next week. But instead, what I want to point out is that is, of course, a Gedankenexperiment, right? A thought experiment. The complex reality of experiments is unfortunately quite more complex. Now, for now, I'm just going to keep this picture as a symbol for experiments. You're going to hear more details about this later. The main message is really there is a big gap between the two, right? It's not always easy to employ your theoretical equations to the complex reality of the experiments. And that gap needs a bridge. And simulations can provide this bridge by sort of putting the complexity but under the simplified approximations of the theory and see what we get. But more importantly, I think simulations can provide a third perspective on your problem at hand and give you new ideas what to look for, both in theoretical as well as experimental work. And there's another advantage of simulations, and that is visualization. You have like a perfect microscope. So here we do an in-silico experiment. The simulations, I'm going to explain you later how they work. I just grow them here in this magic chamber. And then here I plot live the pressure inside this chamber. And you just saw the tissue grew and it filled the chamber. Now we're going to take the piston at the top and just compress it to half its size. What happens is that the pressure, of course, shoots up. But because the pressure shoots up, your growth rate becomes negative, and the number of cells goes down exponentially until we're back to the homeostatic pressure, and the growth rate is yet again 0. And that's exactly what you see here. The pressure shot up, went back down, and comes back to the same steady state as it had before. By the way, you also see those fluctuations here. That's the variance that you saw. I fear that's erased. Sorry, that equation is erased. That's exactly that stochastic noise coming from apoptosis and division inside the simulations, because we have a finite number of cells here in the bottom. Okay, so having advertised why should we do simulations, let me quickly introduce you to my minimalistic tissue growth model. The idea is really here a minimalistic model, so stay simple, put as few ingredients as possible, but add details as the model fails. So in this model, cell is represented by 2 point particles that repel each other by a growth force. And once the 2 particles reach a critical distance, the cell divides and the process starts anew. Other than that, cells behave like sticky soft spheres. That's quite a bit of work to implement that numerically, but it's textbook knowledge. You can look it up in standard colloidal physics type of books. There is one more non-equilibrium contribution. You heard it also already in the lecture, and that's cell death, apoptosis, which we implement just as a constant random removal rate of cells, independent of mechanics. Okay, you just saw what a few divisions look like. If you have more in 3D, it grows to a nice spherical ball, as you would see if you grow them in three-dimensional culture. Okay, what can we do with those simulations? We can really fit them to experiments. And we can use them to visualize the experiments that we've done. So in order to measure this formula here, what we did is we placed tissue spheroids, like in that, into growth media, into a growth solution, but we added large molecular weight dextran to exert an isotropic pressure from all directions. And then we measured the growth rate as a function of time, and that you see here. So here's time, here's the normalized volume, and that's the curves. Now, if you pay close attention to the lecture before, or if you can solve the differential equation on top of your head, these things should grow exponentially. And with a little bit of experience, you see that this is not an exponential growth. Right? I tried hard to fit an exponential there. It just doesn't fit. Interestingly, the simulations fit. But there is already one result that is quite nice, right? The growth does slow down with a bit of pressure. So here's 0 Pascal, here's 500 pascals. 500 pascals is if I balance a little piece of chalk on my finger. Well, a smaller piece of chalk than that. That's 500 pascals. That's very small pressures, okay? Cells react to that. So that made Le Monde already titled here, Le cancer cède sous la pression. That's maybe slightly exaggerated, right? Even though I'm, of course, happy if they like to see our work. Coming back to this non-exponential growth. What we realized, cutting a very long story short, is that this whole thing we learned was assuming that the growth rate, Kd and Ka, do not depend on space. And what we found, both in the simulations and the experiments, is that the growth rate at the surface of the spheroid is much larger than in the bulk of the spheroid. So this here on the left is, you take one of those cancer cell spheroids out of the experiment, you freeze it, you cut it in half, and then you can do some biomagic and label cells that are in the process of division blue. And then you see that there's more cells blue on the outside than in the inside. And of course, I can do the same thing in the simulations, and I see there's more blue on the surface than in the inside. And if you plug that into your equations, you see right away that fits to the growth curves that we had. I'll show you that data later. There's one more interesting thing. Why should they grow more on the surface than in the bulk? Well, naively, you could say that's nutrients diffusing in from the outside, right? However, did I tell you anything about nutrients in the simulations? No, there is none, at least not in those. So that tells you, and that's the beauty of this minimalistic simulations, there must be a mechanical argument of why cells divide more at the surface than at in the bulk. Because that's all there is in the simulations. We cannot prove that that's the cause in the biological reality. But what we can for sure say is that the argument, the mechanical argument exists. And once you think a little bit about it, it's also not so difficult to imagine. If you want to make space for yourself to divide, right, you need to push your neighbors away, which is much more difficult if you're in the center of a crowded room, whereas if you're at the edge of a crowd where you can sort of remove half the strain field. Make sense? So that's a mechanical surface growth effect. That fits the equations quite nicely. So these blue lines here are actually solving these equations under this assumption that you grow more on the surface. There's one more nice thing about it, that when you elevate the pressure, you see it schematically shown here, the growth rate and the surface, whoop, how did I do that? The growth rate at the surface basically doesn't change, whereas the growth rate in the bulk really drops down. So that tells you also that if it were nutrients, then you would, or poisoning of the dextran, you would expect the surface cells to be affected. But no, both simulations and experiments react in a similar way to the external pressure. Now we can quantify things a bit more. This is now data from the experiments, but I'll show you later that the simulations just match on top. This is the growth rate at the surface, which is surprisingly independent of pressure. And here's the growth rate in the bulk of the tissue, so deep inside, where you would actually expect this homeostatic growth law to fit. And you find the nice, well, almost linear dependence as you would hope for. Except there is one little strange thing, right? It's negative everywhere. Well, okay, we were just saying it's linear, right? It can be negative. All it means is that this pH is actually negative. So we have not a homeostatic pressure, we have a homeostatic tension. I thought first this is crazy, until again the simulations helped me to visualize this. Let me stop that video for a second. So what you see here, is a tissue growing in this Gedanken experiment type setup, and the color shows you the age of the cell. So the blue and red, they just divided, the red and white just divided, and the blue ones did not. And you see clearly that they divide more at the surface than in the bulk. But once they reach the piston at the top, this free surface is cut away, so cells you only are left with the net apoptotic bulk, which means you generate tension, negative homeostatic pressure, you pull in the piston, and you reach a new steady state, which is, however, tensile. Or alternatively, if you don't have a top lid, you get a steady treadmilling steady state where cells are generated at the surface and slowly migrate downwards where they then die. And that you could imagine as a process that could sort of stabilize something like an epithelium or so. This is numerically well behaved. The negative pressure is just like a, just another constant. You would in a way expect from a theory, you can just add a constant to the pressure and it doesn't change the dynamics much. More importantly, we can really match the experiments. So here you have the bulk growth rate as a function of pressure, and the points is the experiments, and the dashed line is the simulations. And you see they quite nicely managed to sort of show this non-linear behavior. And if there is some truth to our simulations, they predict a homeostatic pressure of -2 kilopascals. Unfortunately, the experiments cannot reach that because you cannot exert an osmotic tension. Or at least we have so far not thought of a way to do that. If you have an idea to do that, I would be very interested. The other colors are just other cell lines, which interestingly match quite easily. By all what you have to change is to change your time unit by the bulk growth rate at 0 pressure. And then you can extrapolate how other tissues behave at elevated pressures. Okay, keep that in mind. No, there's one more thing. This tension is not unstable, which what you might expect. So if you cut a tissue like this by some sort of virtual laser ablation, first, of course, the tissue is under tension, so it recoils, but that frees new surface, and at the new surface, cells divide again, and the tissue closes again. To me, this is quite reminiscent to when people actually do real laser ablation experiments. Okay, so keep the surface effect a bit in the back of your mind. It will show up again later when we're talking about competition. But let's first start with the easy parts of competition. So why are we interested in cell competition? The whole origin of this idea came from the idea to explain maybe cancerous growth from a mechanics perspective. Of course, you cannot explain everything, but maybe part of the reason why a cancer can grow within a healthy host is just because it is stronger. It has a higher homeostatic pressure. So we plug that, and this idea is not new, that's not just ours. Here's an idea from 1846 to treat breast cancer by exerting mechanical pressure. That's not our suggestion, just sort of telling you that that's not so new. Here's more the idealized Gedanken experiment for that. Imagine we replace that spring by a second sort of evil cancerous tissue that has a higher homeostatic pressure. What happens is that the pressure in this chamber will evolve to a sort of intermediate pressure between the two homeostatic pressures, which will mean, however, that this weaker one will exponentially disappear while the other one will exponentially take over. Again, we can use the simulations to show exactly that. Just for visualization, I'm doing this in 2D. We'll let a small tissue grow, then we will mutate one cell into a stronger cell type by just giving it a higher growth strength, and you see it nicely takes over the compartment. We can even do the extreme comparison. We make one tissue, let's say blue is the reference tissue, which grows fast. So here at the top you have what happens if you grow just this one cell type in a finite box. And you see that the blue cells fill the chamber much quicker than the red cells. However, when you look at the pressure, the steady state pressure of the blue cells is lower than at the red ones. So you have one tissue, blue, which is fast growing but weak, and one tissue, red, which is slow growing but strong. And if you place them in competition, you see here what happens. Even if I start with a chamber full of blue and I add a single red cell, the red population takes over the compartment in a sort of sigmoidal fashion, exactly as predicted by homeostatic pressure approach. And here's the video to that now in 3 dimensions. So the blue tissue is almost invisible there, and you saw how the red tissue quickly took over the compartment. Okay, so far so good. The take-home message is the stronger one wins the competition. And that helps you already explain some phenomena. For example, here, Thomas Riesler, Jean-François, and Marcus Bazin, they looked at metastatic inefficiency. That's the effect that when cells enter, when cancer cells enter the future host, they usually don't grow into a metastasis. They just die off. And the argument is that if they don't adhere well to their neighbors, there is surface tension. Surface tension creates a Laplace pressure, and that kills the cells, which basically gives you a critical radius. If the initial colony of cells is somehow larger than, in these units, 0.5, okay, the metastasis dies off. If it's larger, it takes over the compartment completely. And that sort of allows you to fit the known numbers of how many tumors can arrive at which size. There's one caveat, however. Typically, if you look at especially primary tumors, you don't find a single genotype that took over the full compartment, right? Which you would expect by homeostatic pressure. One tissue should have the highest pressure. It should just take over the place. But that's not what you find. This is called tumor heterogeneity. And a typical tumor looks, like in this cartoon here, a lot of different genotypes and phenotypes all mixed together, okay? So something doesn't quite fit. So we turned again to our simulations to see if we can find something out, if we can somehow match this. So this is just a competition that you've seen before. You have two tissues, one is stronger than the other, and yeah, the red one quickly takes over the compartment, and it nicely fits the simple theory that I wrote down here. Okay, now let's add surface tension. Let's add surface tension by allowing blue cells not to stick to red cells and vice versa. So blue sticks to blue and red sticks to red, but blue does not stick to red. Let's make even the extreme case and take two identical tissues, but that property. Okay? And let's just run the simulation. And what we found to our surprise is that it's neither A nor B that wins. They just evolve to a steady state of a 50-50 mixture. And how that 50-50 mixture looks depends on the initial condition. If I start with a single blue cell, I get this sort of spheroid inside the red tissue. If I start with a random mixture, I get what people in the microemulsion community call a bicontinuous phase, Schwarz P surface. Okay? Why do you get that? And this is stable. Huh? I start from a random mixture of blue and red, and it self-organizes into that structure with a 50-50 mixture. Okay, we have a perfect microscope, so we can look closely and find the origin. For this setup that I showed you first is the easiest one, where we just have a slab-like geometry of blue and red next to it, because that turns it into a quasi one-dimensional problem, which I show here. And now, so here's blue, then red, then blue. It's periodic images, so you have blue, red, blue, red. And now you can look in the simulations how the growth rate looks at the interface between the two. And you see that you have, again, an enhancement of growth directly at the interface. That's a similar effect to what I showed you in the beginning. Because cells don't adhere to each other at the interface, they have an easy time moving relative to each other. So the cells at the interface have an easier time generating space for themselves in order to divide. So you have an excess growth rate at the interface. Okay? Again, you can go plug this into the continuum equations and solve for the pressure, and what you get is relatively straightforward. I skipped the calculations, but you can find them here. You get the solid lines here. So here you have the number fraction of, let's say, red in versus blue. So how much red do you have versus how much blue you have, as a function of the difference in homeostatic pressure between blue and red. So just to walk you through the plot a little bit, here, this guy, here is the red cells have 20% higher homeostatic pressure. And then you go up here, that means they reach roughly an 80% number fraction of the stronger cells inside the blue cells. And the pressure during the whole thing is dominated by the homeostatic pressure of the stronger tissue plus an interfacial term. And that's what you see here at the bottom. So even, okay, this is maybe an interesting little side note. The yellow curves here, the host tissue has a homeostatic pressure smaller than 0. So we're at homeostatic tension. But still, this whole thing can go above 0 pressure due to these interfacial terms, which sort of makes sense because you generate excess cells in the interface, and the pressure has to be high enough to kill off that excess cells in the bulk. Okay? If you look at more complex structures, unfortunately, the simple linear theory fails to explain it quantitatively, but you can still, of course, use the numerics to determine number fraction and pressure as a function of homeostatic pressure difference. And that's the basic structures you get. You get a slab-like lamella phase, you get a cylindrical phase, spheroids, inclusions, and this bicontinuous phase. But of course, you can also find combinations of the two, which I didn't show here, which could be like a bicontinuous phase and a little spheroid in between. But the main take-home message is that lack of cross-adhesion between tissue A and B generates excess cell growth at the interface, which in turn stabilizes coexistence of two different tissues. Now, here we did the extreme case, right? Here we did no cross-adhesion between A and B. Now let's go to the other extreme and wonder about how this tumor heterogeneity could evolve, right? Where probably no cross-adhesion is too extreme. Okay, let's do in-silico evolution. So what I'm doing here, this is maybe a bit of a complex video that I'll show you, but I think there's a lot of interesting things in the next two videos. So here's, you see a phase plot. So we start a simulation which is full of a single type of cells. But these cells are allowed to mutate. Whenever they divide, they are allowed to change either their growth strength or their adhesion strength by a little bit. Okay? And then the color tells you how much cells there is of the different type. And you see that the population, well, first, of course, it spreads out due to the noise we just learned about. But quickly, these cells with low adhesion and strong growth are in an advantage, and you get classical evolution. The stronger phenotype outcompetes the weaker phenotype, and at the end of the simulation, all cells inside the box are of the strongest phenotype here at the bottom right corner. Strong growth, low adhesion. Now, this is quite boring, right? You just get what you sort of expected. The higher homeostatic pressure wins. But what if these things come at a cost? Let's say growing stronger also makes you stick more. Or if you want to stick to your neighbors less, that costs you strength and growth. This is motivated by the cadherin biology. So cadherins, that's the adhesion molecules between cells. They are also signaling molecules. They are also molecules that tell the cell, grow. So you can easily imagine that if the cell downregulates cadherins, that adhesion goes down, but also growth signaling goes down. So these two parameters become coupled. That's the same as putting a line here in this phase space and only allowing evolution along this line. If we make the extreme case of a zero coupling, that means cells can only evolve a stronger growth or weaker growth. Well, of course, they evolve to strong growth. If you make the coupling infinitely steep, that means cells can only evolve in adhesion, and of course, they evolve to low adhesion. But the interesting dynamics show up when we put the coupling between the two to 1. So whenever they become a bit stronger, they also adhere more. Or when they adhere less, they also become weaker. Well, first it seems they go to strong growth and more adhesion, but okay. But then something interesting happens. The population splits up. And we have a stable coexistence of many different genotypes and phenotypes inside the population that stably coexist over time. So here at the end, you see that there's now it came back to a significant population of the original one. There's quite a bit of strong growth, strong adhesion, but the whole intermediate regime is populated. The cool thing is we can understand this again by this sort of number balance theory that you learned about today, right? Just add the mechanics part that you will learn next week. What you have to do, though, is you have to say there is some term that is proportional to the interaction between the two phenotypes, okay? Because we said this is because A doesn't adhere to B or vice versa. That, if you write continuum equations, you typically write that as a term that is proportional to the population of one cell type with respect to the other one. So for two different cell types, let's say you have only two types, you can do this analytically, and you find a stable fixed point at, okay, forget the equations here, at some number that depends on parameters that you can measure in the simulations. And then you reproduce what we find in the simulations here. So here I show what happens if you change the self-adhesion. So you take two tissues, you keep the host tissue constant, and you change the invading tissue to a different adhesion strength. And you also change the growth strength accordingly. And what's the stable, steady state you get? And again, you get, in many cases, coexistence, which is highlighted here by the intermediate number fractions, right? If the number fraction is 1, that means the original host just took over the compartment. If the number fraction is 0, means the host lost and the cancer took over the compartment. But in many cases, we find stable coexistence between the two tissues. And the point where the coexistence lies is really dominated, is exactly described by this stable fixed point that it comes from the mixed term that I showed here. So from the cell population interaction. Okay? So I think that's quite interesting because it tells you that simple mechanics are sufficient to drive stable coexistence and divergent evolution. I think that's quite cool. Now, because we learned today about these waves here, I wanted to tell a little, like I told you, I'm going to do a little roller coaster ride through those simulations, okay? So now if you sort of if I lost you at some point, now is a point you can jump back in. So I'm going to talk about this kind of wave or front propagations that you just learned in the lecture. The point, I'll tell you a little bit the story. The point is that when I look at quasi-one-dimensional systems, I don't see diffusion. But I still see propagating fronts. So I was fascinated and I wanted to simulate this and understand this. So here is the simulation version. Look at the bottom one first. So here you have a stronger tissue in blue on the left and a weaker tissue on the right. So the homeostatic pressure of the red one is lower than the homeostatic pressure of the left one. And you see a nice constant velocity invasion of blue and red. And now in order to get more statistics, we invented a co-moving simulation setup. We call it treadmilling simulations. That's what you see at the top here. And so you can sort of imagine that you have an infinite system and you're just moving your microscope with the tissue front. Okay? But that's why it looks like the tissue doesn't move, but you see the substrate moving a bit. Okay? So the cool thing is you can combine this theory here with this guy here. And then you can even put the diffusion coefficient to 0 and you get a nice solution to the equations, which is without any adjustable parameters, the blue curves that you see here. So here's, for example, the velocity at the interface relative to the position away from the interface. And then you see that cells at the interface are moving at a finite steady state velocity. That's this V0 that we got somewhere here, right? Except not by the diffusion, but by the mechanics coming from here. This velocity decays exponentially as you move away from the interface. That makes sense because the front is moving and far away the tissue is set on the substrate. The stress evolves from the homeostatic pressure of one tissue to the homeostatic pressure of the other tissue. And again, the analytical solution, I would say, almost perfectly matches the simulation results. There's one more curious thing which with the original analytic description could not tell us, was that actually in 2D, this also works. So if you have a very large system, you still have an almost flat interface, almost flat, not flat, that propagates to the right, right? And that, even though there is no, the adhesion between blue and red is the same. So in principle, from sort of equilibrium mechanics, you would think that they would perfectly mix. But this whole dynamics of growth flattens the interface. What happens is if you have a bulge of one tissue growing out into the other, so here's tissue A, here's tissue B, well, this one has an easy time to expand like that and flatten out the interface again. Okay, that's what I thought back in 2016. Then another student from Jean-François saw my paper on this, and he said, well, that's a nice hand-waving argument. Let's do a proper linear stability, or let's skip that. Let's do a proper linear stability analysis of this kind of flat interface. And what he finds is that there's a lot of ways where this interface can be linear unstable. Okay? I won't walk you through the equations. Maybe you will have the luck to hear Guillaume-Salbreux to talk about that. So that's Williamson and Salbreux, PRL 2018. You see we're rapidly moving towards today. And he showed that, for example, if the tissue here on the left has a motility force pushing it to the right, then this should be unstable. Now we plug this into the simulations, and this is what you see. So this tissue on the left is moving to the right. We're just in a co-moving reference frame here. And you see here a nice L/3 linear instability, right? Except that this linear instability seems to be sort of limited by higher order terms so that the amplitude of this instability doesn't grow beyond a certain finite maximum value. And there's another nice side thing I want to mention here. This is perfectly symmetric, right? If I just would show you this snapshot, it would be impossible to tell whether it's red invading blue or blue invading red, right? They are sort of, the instability seems to be symmetric. And the instability shows up because the amplitude becomes larger and larger the more you increase the motility force. Now, Guillaume predicted another type of instability, which is related to viscous fingering. It's saying that if this prefactor here is smaller for the tissue that gets invaded, for the experts, that means if this guy is smaller, the effective long-term viscosity becomes larger. So effectively, the tissue you're invading has a larger viscosity. Then you get another type of instability, and that looks quite different. It's very dynamic. It doesn't reach a real steady state. The amplitude becomes steady. The total width of this interface becomes steady. But as you just saw, the dynamics are, not constant, right? There's no clear, well-defined wavelength. We also studied the structure factors and so on. And here you don't see anything, whereas in the other here you see a clear structure in the structure factor, whereas in the other tissue, you don't see any well-defined structure, right? And it's, I think you see that this is quite dynamic, right? I don't need to argue about that. Okay. That's pretty much arriving today. So I fast-forwarded you through 10 years of using particle-based simulations to study tissues. There's little things I want to tell you on scope, what else you can do with this kind of model. One is study bacterial growth, where mechanics play less of a role, but we can add nutrient dynamics in a similar way as here, just coupling the nutrient field directly into the growth field K here. And here, bacteria are much easier to match because they're sort of less complex in their behavior. So this is experiments, this is simulations, and you see that you can quite nicely match the growth of in-silico bacteria with real bacteria over time in a quantitative fashion by taking care of nutrients. And the coupling is relatively straightforward. Another thing you can do is you learned in the last week's lecture that people are thinking that maybe growth and buckling of growing sheets is at the cause of a lot of patterning in biology, right? That, for example, there's the idea that the gyrification of the brain is because the cortex grows faster than the white matter, right? let me tell you that there is a lot of problems with that work in the literature, but that's a separate discussion. The key point is there's still, that's a hypothesis that you want to take a look at, right? And again, you can take those simulations that I showed you before, and you just add a potential that forces the cells to be in a two-dimensional manifold. They can still bend like a typical membrane, but only on a larger scale. So you get a growing membrane with a bending rigidity, and you see that it nicely buckles in sort of complex structures. And we are also using the same kind of approach to try to tackle something like brain folding, and yeah, there's a lot of difficulties going on there. Okay, with that, I'd like to summarize. I showed you this minimalistic growth model, where again, like I said, I mean, the idea is not to grasp the full complexity of the real biological cell, but to have a minimalistic model to get insights into mechanics of growth. And I hope I was able to convince you that these kind of simulations, even though simplistic, can give you ideas of what to look for, both in experiments as in simulations, as in theory. I showed you that we can match these experiments of growing spheroids, that we get interesting surface interactions at propagating fronts, and interesting structures if we do competition in 3 dimensions with surface interactions. But the main message, actually, I guess, is both in my talk and the whole lecture, that there is a lot of interesting physics going on in the physics of growth, and maybe a bit differently, that computer simulations can provide a powerful tool to explore these new physics that we're looking for. Okay, with this, I would like to thank, of course, a lot of people who did this, right? First of all, I would like to thank Jean-François Joanny for introducing me to the whole subject. That's where we started the simulations. But of course, I should also thank a lot of people who worked on this. Most of the simulations I showed you today were done by Tobias Büscher in the back here, and Niels Podewitz in the back there, and Raphael Hornung standing in the front there. This is, by the way, not the continuous team. This is just a little family reunion we had for some Christmas. And yes, thanks to all of you for your attention. And if you have questions, please ask or send me a mail and I'll answer. Thank you.